So, welcome to our new and maybe last chapter. Maybe we will have time for a bit of one more just before the end of the semester. But however, this is so the sixth chapter in that semester. It's some classical examples in partial differential equations. Okay, and we will do some lab next week about this. But before, we need to remind a few things. All right. So first, we're going to work a bit just through one or two examples on things we did last year at the beginning of semester 3 about partial differential equations. So, a few examples involving substitution and chain rule. Okay, we're going to practice that again. So let's begin. A simple partial differential equation of the kind I could have given you last year, right? So let's say I want to solve this equation. d2f over dx dy is equal to 0. And my unknown is the two variables function f of xy. Remember what it was? So how do we write that? We can write that it's the derivative of df over dy that is equal to 0. The derivative according to x is equal to 0. So that means that that inner function does not depend on x, so it must be a function of y only. So we can write that df over dy must be some function of y only. Okay, every time I've got my partial derivative of f or functions of x and y. Right, so if now the partial derivative according to y of f is some function of y, it means that f of xy, well, there must be a part that is this function of y. So as this was arbitrary, well, we can say it's going to be called, let's say, g1 of y, which technically should be a primitive of the g of y I have written, but as this was an arbitrary function, it's just going to be an arbitrary function of y, and I can always add anything that depends only on x, because if I differentiate this with respect to y, it's just going to be 0, and then it's going to disappear. Right? And so if you choose G1 and G2 to be sufficiently continuous, let's say twice continuously differentiable, we've got a C2 function of R2. Okay, so that was just to remind you of things we did last year for that one, for that example. Second example, more complicated. Now we want to solve x squared d2f over dx squared minus y squared d2f over dy squared is equal to 0. Okay, and what we learned last year was that these kind of things we could only solve them if we were given some rightly chosen substitution. Okay, so here we're going to use substitution u is equal to x times y, and v, sorry, that should be a v is equal to y over x. Okay, we should check that it's a valid substitution by checking whether it's invertible and so on. But let's assume this is okay, right? We should do the Jacobian and check for the local inverse theorem and then the global inverse. But let's say it's all right and we are allowed to do that. That's not what I want to do here. What I want to do is, how do I put this substitution in my equation? Well, we must say that what does it mean to have a substitution? It means that I had my function of xy and I'm going to create a function of my new variables u and v. Okay, so that what does that mean? It means that it's going to be, well, some function g that depends on u and v, but u itself depends on x and y. Okay, and u being x times y, v being y over x. V of x times y. That means, and that's just going to be very general, if I want to take the partial derivative of f according to x, it's the same thing as the straight derivative, remember those subtleties, of g of u of xy, v of xy. Okay, Partial derivative because it indicates that I'm going to take the derivative of f according to the first variable, but that really means in that case differentiating with respect to x. It's not going to be the derivative of g according to the first variable, but the derivative of the expression where I would have the expression of g, where I would have substituted u and v by their expression depending on x, y. I want to differentiate that one according to x. Okay, so you have that straight variable. So just to remind you, what was that chain rule? So you have to be able to be very confident using that this year, but I hope it's going to seem to you much simpler than last year. So chain rule, du over dx times dg over du plus dv over dx times dg over dv. Okay, g has two partial derivatives. G as a function of u and v has two partial derivatives according to its first variable, so that's d over du, and according to its second variable, that's dg over dv. Okay, and I just wrote the chain rule that we have, right? So that's just going to be du over dx. Let's remind us that u was x times y and v was y over x. So du over dx is just going to be y times dg over du, which itself is still a function of xy, v of xy, plus dv over dx, that's actually going to be a minus, okay, minus y over x squared dg over dv. Okay, all right. So let me just write that a bit more concisely. D over dx of f is y dg over du minus y over x2 dg over dv. Okay, in my equation, which I remind you was this one, okay, so x2 d2f dx2 with y2 d2f dy2, I have to get the partial derivatives or order 2, so calculate them as I'm doing it. All right, so we're going to need d2f over dx2, that's just the d over dx of the previous one. So that's just going to be this derivative according to x of the previous expression that we just obtained. What depends on x and y? U of xy, v of xy. Okay, so we shouldn't forget that. Minus y over x2, that also depends on x, all right? dg over dv. Okay, so let's just perform our chain rule again. So that's y here does not depend on x, so that's just y times derivative according to x of this one. So that's just going to be du over dx d2g over du square plus dv, so I had my y as a factor, over dx times d2g over dv du. Okay, so that's that part here. So that part here really corresponds to the derivative of this one, right? Let's go for the second one. So second one is just I've got y over x2 that depends on x, so I have to make d over dx of y over x squared, so that's just going to be minus 2y over x cubed, so plus 2y, plus because I already had a minus, over x cubed dg over dv. Okay, this is a product of functions, so that's really like u times v. So this is really like u times v. So if I differentiate it, that's going to be u prime. That's what I wrote here, u prime v plus v prime. What's I'm going to write u. So I get the u, it's the minus y over x2 that doesn't change, and derivative according to x of dg over dv. So that's just going to be du over sorry, I'm trying to, okay. I've lost du over dx d2g over du dv minus y over x2 dv over dx d2g over dv squared. Okay, take some time after the class to be sure you know how to redo these calculations, right? I'm going quite fast now. So let's find it again. All right, so what we have, let's just write du over dx is again going to be y, dv over dx minus y over x2. So I've got dg over, this one doesn't change, this one du over dx, that's y, dv over dx minus y over x2. So what do I have left? So I've got y square d2g over du square plus, well, minus y square over x square d2g du dv. Then I've got plus 2y over x3 dg over dv minus, so y square over x2 d2g du dv. Well, that's the same one as this one, okay? So maybe I can put a 2 here and erase the one that I've just written here. Okay, then I've got, so what was that? That was this term. And then I've got the v2 one, so minus y, so plus, sorry, y square over x to the 4 d2g dv square. Okay, all right, so that was for my first partial derivative of the second order. You should do the same thing for the partial derivative of the second order for you should do the same thing for d2f over dy2. Let's say that you will take some time at home to redo the calculations, and you should find that it's going to be equal, well, if you perform exactly the same kind of calculations, to, well, let me copy that correctly. So x2 d2g over du square plus d2g 2 times d2g over du dv plus 1 over x2 d2g over dv square. Okay, that was a slightly simpler one because the derivative according to y of v is much simpler. Okay, so that if you put together all the if you substitute in the original equation, which was x squared d2f over dx2 minus y2 d2f over dy square, that should simplify, and you will obtain something like 2y over x dg over dv minus 4y square d2g du dv. That's still problematic because I have a mix of x, y, and uv. So let's substitute that by the things we know. So y over x is exactly the v. So 2 times v dg over dv. And the y square is exactly, what is that? That's exactly u times v, all right? Minus 4 u times v d2g du dv. Why is that slightly simpler? Let's have a look, okay? Because I can rewrite this as 2 times v times derivative according to v of g minus 4 times u d2g over d. Okay, and that should be equal to 0. Okay, so it's really something very similar to what we had to solve earlier. So it's 2v times the derivative of something is equal to 0 for all values of d. That means that this something must be only a function of u. So we get that g of uv minus 4u times d2g over du is something that depends only on u for an arbitrary function. Okay, k is an arbitrary function, right? So let's see what we have next. So we have to solve g minus 4u dg over du, not d2, dg over du is equal to k of u for an arbitrary k function. And so what is that kind of equation? It's just going to be, we have just one first order differential. Well, it's just along u, but then that's fine. So we have, you know that we can go for the homogeneous equation. So homogeneous equation would be the one where I want to solve. Sorry, I had a 2 here. So it's a 2 here, where I want to solve 2u dg over du is equal to the g function. All right, so where k is equal to 0. So that makes dg over du is equal to 1 over 2 times 1 over u. So that's dg over du divided by g, sorry, is equal to 1 over 2 times 1 over u. So we get some logarithm here. Ln of g is equal to 1 over 2 ln of u plus some constant. So that, you know, that's the log of square root of u. And so you know that when I apply my exponential, that's going to be, well, a second constant technically, times the square root of u. Okay. So that was my homogeneous solution. So then to find the non-homogeneous solution, I'm going to perform a variation of parameters. Okay, so you remember, I'm going to say that g is actually something like k of u times square root of u. My constant is now considered, well, where we want to see if we find a constant, a non-constant function in front of it, what should it do? So I'm going to have, if I substitute that in my equation, so let's say I have divided by 1 over 2u, so that I've got nothing in front of my derivative. So that was equal to, I said some function k of u divided by 2u. Let's call that some L of u, as k of u was supposed to be arbitrary. Okay, so if I put g as k of u square root of u, then I'm going to have dg over du is going to be k prime square root of u plus k divided by 2 square root of u minus 2 square root of u, sorry, k of u, minus 1 over 2u times k of u square root of u, that's my g function, should be equal to some function of u. And of course, these terms cancel. That's how I know that it has, it's simplified. And so k prime square root of u is equal to L of u, so that k prime is some arbitrary function of u divided by square root of u. And, well, all this just to say that that k should be, well, a primitive of this, L of u divided by square root of u, which just gives me some constant plus an integral, well, a primitive of this arbitrary function of u, which just gives me actually an arbitrary function of u, right? So let's maybe call that h of u, and I've got my constant. And so what do I have now? Let's reconstruct my g. Well, don't forget that g is the function of uv, so actually my constant k here could depend on v. It wouldn't change anything, right? So k of v times square root of u plus h of u, some function of u times square root of u, which is well, we can keep it that way. Yeah, we can keep it that way, but it's really a function of u, so it doesn't really matter. So that's so that was a plus here. So maybe we could call that I don't know how many functions I've introduced here. So h2 of u, right? So in the end, this is my g functions. This is what they're going to these are my solutions to my partial differential equations. But then if I want to write it as function f of x, y, that's just I will have a function that depends on y over x times a function times some square root of x times y plus some function of x times y. Okay, possibly multiplied by square root of x times y, but it's already included in that one. Okay, and these are arbitrary. Okay, so these are some very long exercise. So yeah, that's it.